Welcome to my talk on HTTP message signatures. My name is Victor Lyuboslavsky. I've been in tech for over 25 years and I'm currently a principal software engineer at Fleet Device Management, where we make endpoint telemetry for corporate security teams and device management for corporate IT teams for their laptops and mobile devices. So if you ever try to improve security in a real organization, you know it can be a struggle. You come up with what seems like a good idea, but the moment you share it, someone says, "Oh, that's too custom, that's too complicated, that'll break our infrastructure, and besides, we don't have time for that." It's frustrating. You're not trying to slow anyone down, you're just trying to make things safer. That was me a few months ago. Our API used a token stored on a file on a client. This means anyone could copy that API token and make requests. We wanted to make it more secure. I proposed a custom security solutions to the team and was met with questions and doubts. But that rejection actually made me think harder and led me to something better. I really dug into the security solutions in the industry and I found the standard called HTTP Message Signatures, RFC 9421. It turns out the solution already existed, I just wasn't looking hard enough. So what does it do? So you sign receipts, contracts, and maybe your kid's permission slip. Your signature means this came from me. But on the web, most signatures are unsigned. Anyone could forge them. HTTP message signatures change that. They make digital communication accountable. The server now knows that the message actually came from the client, the right client, and it wasn't modified by someone. So why do we need this? When two systems talk over HTTP, the server sees a request, but it doesn't really know who sent it or if the message changed on the way. The server doesn't know if a bad actor is impersonating the client or if a bad actor modified the contents of the message. Let's take a look at a diagram. So to trust the message, the server needs some way to verify that the message came from the client. That happens with keys. So you've got the public key and the private key here in this example. In this diagram, the client sends the message, signing with its private key, sending it over to the server, and the server verifies the message with the public key that it has. The client signs specific parts of the request. We'll get into the details in a few minutes, but basically the signature tells the server who sent the message, that the message hasn't been tampered with, and which parts of the message are covered by the signature. So where exactly is this signature in the HTTP request? Well, HTTP message signatures are just added to the HTTP request headers. This leads to other use cases. For example, since we're just updating the headers, this means that the signature can be added by a proxy, as shown in this diagram. The client could be a legacy system, and we can simply effectively wrap a proxy around it to make that whole communication more secure. And this is what we're doing in our system, where we have a legacy C++ client, and then we pass it through a proxy to add these HTTP signatures. What about alternatives? How do HTTP message signatures compare with older security approaches? Let's start with API keys. They're simple but limited. API keys are like shared passwords. You include them in a header or query parameter, and the server knows someone with that key made the request. API keys are simple and widely used. But here's the problem. API keys only authenticate the client. They don't protect message integrity. If a proxy, cache, or malicious actor modifies the message in transit, there's no proof of what changed. The server can't tell whether the message has been tampered with. So with HTTP message signatures, instead of just authenticating the connection, they also sign the message itself. So the server can verify not only that who sent the message, but also that nothing was modified along the way. What about JWT, JSON Web Tokens? They're everywhere, right? JWTs became the de facto standard token format in Auth 2.0, where they're sent in the authorization header. That pattern is now universal for most API tokens, even if you don't use OAuth explicitly. The problem is that a JWT only signs its own contents, right? These contents over here. It doesn't sign the actual HTTP request. If someone intercepts a valid JWT, they can use it in a completely different request. They could change the method from get to delete, modify the request body, or alter headers. The server will validate the JWT and accept it because the token itself is legitimate. So a JWT is basically a fancy API key and has most of the same problems. What about mTLS, Mutual TLS? This picture over here shows the mTLS handshake. mTLS is the gold standard for authentication when both client and server present certificates during the TLS handshake. It's built into the TLS protocol, it's fast, it's well supported across operating systems and browser. But mTLS is all or nothing. You can't easily enforce it on just one endpoint or route, and it's typically applied to the entire connection. It also requires TLS termination, so in this example, you would normally have a load balancer over here between your application server, and that load balancer would be terminating the TLS. And in our example, if you want the application to actually know what certificate it is, the load balancer would have to somehow forward that certificate to your application server. So this makes mTLS difficult to deploy in many real-world architectures, since the load balancer effectively becomes part of the application. So HTTP message signatures mainly work at the application layer. They don't care where the mTLS or the TLS terminates. You can verify signatures at the application server, apply them per route, and enforce them selectively based on your requirements. They're much more flexible. So who is using HTTP message signatures? They're actually gaining real traction across the industry. Here's who is using them and why. OpenAI signs requests from their ChatGPT agent. So you've probably heard about complaints about small sites being overwhelmed by AI bots. Without signatures, it was nearly impossible to tell which AI company was responsible for all that traffic. Now, CDNs and firewalls can verify that traffic actually came from OpenAI by verifying their signature, not some impersonator trying to abuse OpenAI's reputation. And speaking of CDNs, Cloudflare has built HTTP message signatures into their verified bots program. Site owners can now whitelist legitimate bots while blocking the fakes. So no more relying on IP ranges that constantly shift or user agent strings, headers that anyone can spoof. The cryptographic signature proves the bot's identity. So if you have a site, you can choose which bots you allow to access your site. Let's briefly cover two more. So Mastodon uses HTTP message signatures to protect the federated network. When one Mastodon server receives activities from another, it requires cryptographic proof that the sending actor actually authored the request. Amazon requires HTTP message signatures for third-party payment providers accessing their selling partner API in the EU. And this isn't optional. It's an EU compliance requirement. So we're also seeing new standards being built on top of HTTP message signatures. We've got this one over here, RFC 9635, finalized in October 2024. It's the Grant Negotiation and Authorization Protocol. Think of it as a more flexible alternative to OAuth 2.0. There's also a draft for HTTP message signatures directory. This draft solves the problem of key exchange. It defines a well-known endpoint where clients can publish their public signing keys. So who is not using HTTP message signatures? Well, most companies that aren't using the standard already have something that works. They built their own solution years ago, and migrating to a standard may be difficult and not high on their priority list. So Apple's MDM, Mobile Device Management Protocol, uses a detached CMS, cryptographic message syntax signature with a custom header. GitHub signs their webhook payloads with HMAC SHA-256 and a shared secret. So these custom approaches largely accomplish the same goal, but they're not interoperable, which is why standardization matters. Here's the real value of a standard like RFC 9421. You don't have to decipher someone else's custom security scheme every time you integrate with a new API. So right now, if you want to verify GitHub webhooks, you have to read their docs, implement their signature verification with their specific header format, and then write custom verification logic. Different header names, different signature formats, different canonicalization rules. Every vendor has been reinventing the wheel. With the standard that we have now, libraries can implement signature verification once. Security tooling gets better, security audits become easier, security becomes more accessible, and not a huge pain in the butt. Now, let's dive into the actual technical nuts and bolts of HTTP message signatures. RFC 9421 is a proposed standard from the IETF, Internet Engineering Task Force. The name proposed is a little confusing. Proposed standard means it's fully approved, stable, and ready to implement. This is the same standard level where almost all internet protocols live: HTTP, TLS, DNS, etc. Basically, once there's a number, it's a standard. Here's a sample HTTP message. There are two headers to sign request. We've got signature input and then the signature itself. So signature input, specify what you're signing, which headers, which parts of the request, and metadata like creation time and key identifier. And then the signature contains the actual cryptographic signature for those components. So which parts of the message you can sign? Well, you can sign any HTTP headers, right? Any header from the request, like content type, authorization, etc. And header names are lowercase for the standard. And then you have got these derived components prefixed with an ampersand. You pick which components to sign based on what matters for your security. For example, signing with @ method prevents someone from changing a get to a delete. But what about the body of the message? Well, you actually don't sign the body directly. Instead, you calculate a cryptographic hash of the body and include it in a content digest header, which is another standard, RFC 9530. Then you sign that header. So this content digest header becomes one of the signed components. So the verifier not only needs to verify HTTP signatures, it also needs to verify the hash of the body, right? So that way, if someone tampers with the body, right, either the signature or this hash is not going to match and the verification will fail. We also have metadata that can be part of the signature. So in this example over here, we've got created and we've got key ID. So created is when the signature was created. Key ID is which key to use for verification. So these metadata parameters are part of the RFC standard and are included in what gets signed. Metadata can also include expires, a nonce, algorithm of the signature, and an application-specific tag. So now that we know what goes into the signature, let's touch base on how the signature is created. So the client that's creating the request builds a signature base from the selected components. Each component, as you can see, gets its own line with the component name in quotes, a colon, and a value. There's a new line between the fields. Each line, the last line, contains the actual signature parameters, and they must match, right, exactly what's covered by the signature. And this whole text gets signed with the private key. So the key ID parameter in the signature identifies which key to use down here. This supports key rotation, so you can even include multiple signatures in a single request. The one with the old key, one with the new key, during rotation periods. Let's take a brief look at the supported algorithms. The RFC initially registered all these algorithms, but this list is extensible. IANA maintains the official registry where new algorithms can be registered, so that standard can evolve with future algorithms. Now, you might be wondering, with asymmetric algorithms, how does the server get the client's public key so you can do the verification? So the RFC doesn't mandate a specific method, but here's a few options. So you can register the client's public key with the server out of band, like use an API portal, configuration file, database. You can use this new HTTP message signatures directory draft to publish the keys in a well-known place if you control domain. You can also use X509 certificates and reference them via the key ID in the metadata field. That's what we're doing. We're using certificates, so we're using another protocol to issue certificates to our clients and then using that certificate key pair for the signing and verification. All right, it's live demo time. We've implemented a simple demo app that demonstrates how to sign and verify HTTP requests with RFC 9421 in Node.js. The app is available on GitHub. So there's many JavaScript libraries that implement HTTP message signatures. This is just a raw dump of the results when I search on NPM. Many companies also don't use libraries and do their own implementation of the standard. So for our demo, we chose this one down here because it seemed like cleaner, more intuitive API. It's got good documentation and examples. It is pretty stable, and it's got better compatibility with Express. All right, let's give this a shot. If I'm pressing the right button. There we go. Okay. Device management at work right there. Let's dive in. So before sending a request, we have to exchange the key. So we're doing that with a separate API endpoint. So I'll just do npm run demo and roll. And so we exchange the keys. So now the client shared its public key with the server. Now let's do a good run. npm run demo good. Let's do that. So the client created a request. It has signature input. It sent to the server. The server authenticated correctly. Everything's good. Now let's do another demo. npm run demo bad method. So in this case, the client created a request, but then someone in the middle changed the put to a post. The server then said basically couldn't verify the signature. It failed. So let's do one more. npm run demo bad replay. So in this case, the client sends the first requests, everything goes through, and then an attacker captures the request and tries to replay it, tries to send it again. And we'll get into the details later, but basically the replay does not succeed because the server was checking the nonce. Let's go ahead and take a look at the actual code. So we've got the demo client, the client that sends the requests, right? It creates the content digest down here. Content digest, we use a standard sign method here with this algorithm. We generate the nonce. And then this is the key. This is all we have to do here. We call this library function. We specify the KID algorithm, the signer from up here. And then we tell the library what we want to sign, one of these two, and then we give it the metadata that's going to be signed. So that's all it for the client. It's pretty straightforward. Now let's look at the server. So the server has to verify the signature. So we got some validation checks. We're looking at content digest header here. We have to transform the express request to the library's request interface, which is basically like this. Then we kind of figure out the algorithm we use, and here's the library method, verify message. So the key here is the key lookup, right? We have to know which public key we're going to use to verify. We get it from our database, get key over here. We do some validation here. We validate the nonce, which we'll get to when we talk about replay later. We support multiple algorithms here for verification. And then we use the standard signature verify crypto method. And this is what we return. We return the key ID, the algorithm we use, and this verify that we created here, which is going to use the standard method. And then we pass in that message. So that's how we verify. Okay, let's get back to our presentation. All right, let's talk about replay. A replay attack happens when someone captures a legitimate request and sends it again to trigger the same action a second time. Think of it like photocopying a signed check. The signature is real, the request is valid, but you're using it in a way that wasn't intended. HTTP message signatures protect against tampering, but they don't inherently prevent replay. An attacker who intercepts a signed request can replay it from any machine. They don't need your private key. They just need the complete request with the signatures headers intact. Let's take a look at a sequence diagram. So consider this scenario. You send a signed API request to transfer $100 up here. The signature proves the request came from you and hasn't been modified, but then an attacker captures it and sends it again and again. If the signature is valid and you don't have replay protection, right, then that money gets transferred again. So we need to add replay protection. So the key is to make sure each signature is single use or time limited. The standard way to do this is with a combination of a timestamp and a nonce metadata parameters. So you can use a created or expires timestamp to limit the time window when the signature is valid, typically 5 to 10 minutes. But then for critical operations like money transfers or password resets, you need to add a nonce. A nonce is a random value, and the server tracks recently used nonces. You can use like a Redis cache or something like that, and then reject any requests that reuses a nonce within the time window. Finally, let's discuss performance, which matters when you're operating at scale. So HTTP message signatures shift cryptographic work to the application layer. Every single request requires signature verification at your application server, not at the network edge or load balancer. This is different from connection level security like TLS or mTLS, where the cryptographic operations happen during the initial handshake and subsequent requests on that connection are relatively cheap. With HTTP message signatures, you're adding cryptographic operations on every request. Your application servers handle this work, not your load balancer or edge infrastructure. So, does your API need message level authentication? Not everyone needs it. If you're building a simple internal service with API keys over TLS, you're probably fine. But there are specific situations when message signatures solve real problems. Ask yourself these questions. How easy it is for someone to modify the message between your client and the server, and if it happens, how big of a security problem is it? Could it happen internally, like between your load balancer and your application server? mTLS may be possible to solve your security problem, but you can't use mTLS everywhere. Maybe you have a public-facing API where client certificate management is impractical, or you need per endpoint authentication control, or not all or nothing connection security. Message signatures work at the application layer, giving you more flexibility. Then, are you integrating with a federated system? If you're building something like Mastodon, where servers need to trust messages from other servers they've never seen before, message signatures with published private keys solve that problem quite cleanly. Then, they want a standard instead of custom schemes, right? Tired of implementing different signature verification of every vendor's API? Want your clients to use a standard approach instead of your custom homebrew scheme? If you answered yes to any of these, HTTP message signatures are worth evaluating. If not, simpler approaches may be a better fit. So the standard exists, the libraries are available, major companies are already using it. The barrier to adoption of HTTP message signatures is lower than you think. That's it for my presentation. I've got some links about my company, we are hiring, and some links how to find me. Thank you, everyone.